Graph neural networks, GNNs, have become increasingly popular in various applications, but their widespread use has raised concerns about privacy protection. The graph data used for training GNNs may contain sensitive personal information, which can be encoded in the learnable parameters and lead to privacy leakage when the trained GNNs are deployed. To address this issue, machine unlearning for GNNs has emerged as a technique to remove certain personal information from a trained GNN. Existing certified unlearning approaches for GNNs have limitations, including low flexibility and being designed for specific GNNs or optimization objectives. To overcome these limitations, this paper proposes a flexible framework of certified unlearning for GNNs, called IDEA. IDEA aims to develop a certifiable unlearning framework that can flexibly unlearn personal information in graphs and generalize across GNNs. The paper identifies 3 challenges in developing IDEA: characterizing node dependencies, achieving flexible unlearning, and obtaining certification for unlearning. To tackle these challenges, IDEA proposes to model the intermediate state between the optimization objectives with and without the instances to be unlearned. 4 different types of common unlearning requests are instantiated, and GNN parameters after unlearning can be efficiently approximated with flexible unlearning request specifications. IDEA provides a novel theoretical certification on the unlearning effectiveness, which brings an empirically tighter bound on the distance between the approximated and actual GNN parameters compared to other existing alternatives. The paper contributes to the problem formulation of flexible and certified unlearning for GNNs, proposes IDEA as a flexible framework, and conducts comprehensive experiments on real-world datasets to verify its superiority over existing alternatives. The paper uses notations such as bold uppercase letters for matrices, bold lowercase letters for vectors, and normal lowercase letters for scalars. It represents an attributed graph as G equals V, E, X, where V is the set of nodes, E is the set of edges, and X is the set of node attribute values. The paper focuses on the node classification task and optimizes the parameter theta of the GNN model F with K-message passing layers. The authors propose a flexible framework for certified unlearning in graph neural networks, GNNs, which provides a theoretical guarantee of unlearning effectiveness. They adopt the epsilon-delta certified unlearning criterion, which relaxes the requirement of unlearning by a small threshold epsilon and a probability delta. The framework, called IDEA, aims to achieve flexible and certified unlearning for GNNs by approximating the change in the learnable parameter theta asterisk operator during unlearning. The authors instantiate 3 types of unlearning requests: node unlearning request, edge unlearning request, and attribute unlearning request. They define delta G as a potential combination of all types of unlearning requests, which includes nodes, edges, and attributes to be unlearned. To bridge the gap between the original training objective and the perturbed training objective with information of delta G being removed, the authors propose a formulation to characterize the intermediate state. They add an additional term to the original objective function, which includes LAD and L sub. LAD represents the loss function with the information of delta G being removed, while L sub represents the loss function with the original information. The authors introduce a novel theoretical guarantee on the effectiveness of IDEA as the certification. They define phi k as a function that takes a node and a graph as its input and outputs the set of nodes in the computation graph of the input node. They then propose a formulation to characterize the intermediate state, which includes V1, V2, V3, and V4. These sets represent the nodes whose computation graph includes the nodes, attributes, and edges to be unlearned. The authors prove the optimal equivalence between the original training objective and the perturbed training objective with information of delta G being removed. They show that the optimal solution to the perturbed training objective can be approximated by the optimal solution to the original training objective with a first-order infinitesimal residual. This approximation strategy relies on the assumption that the sets V and V are disjoint for I, j element of 1, 2, 3, 4, when I does not equal j. However, it can also handle cases where such an assumption does not hold. The author's framework provides a flexible and certified unlearning approach for GNNs, which can handle various types of unlearning requests. The theoretical guarantee of unlearning effectiveness ensures that the framework can provide a reliable and efficient unlearning process for GNNs. IDEA is a flexible framework for certified unlearning in graph neural networks, GNNs, focusing on node, attribute, and edge unlearning. The framework utilizes a novel approximation approach to achieve efficient unlearning, and it also provides a certification mechanism that ensures the closeness between the ideal and approximated unlearned parameters. The certification is based on the L2 distance bounds between these parameters, which are derived under common assumptions about the loss function. The authors evaluate the performance of IDEA across various GNN models, including linear and nonlinear models, and different graph datasets. They compare the derived bounds with existing certified unlearning approaches, such as CEU, and demonstrate the effectiveness of IDEA in terms of bound tightness, model utility, unlearning efficiency, and unlearning effectiveness. The experimental results show that IDEA achieves better bound tightness and efficiency compared to other baselines, while maintaining the utility of the original GNN model. In this study, the authors present a novel framework for certified unlearning in graph neural networks, GNNs, named IDEA. This framework aims to address the challenges of unlearning in GNNs, particularly focusing on node, edge, and attribute unlearning tasks. The authors evaluate the effectiveness of IDEA through a series of experiments on 5 real-world datasets and compare it with various baselines, including retraining, random, BEKM, BLPA, and CGU. The evaluation results indicate that IDEA achieves competitive utility compared to other baselines, with only minor sacrifices in performance. Furthermore, IDEA demonstrates superior unlearning effectiveness in both node and edge unlearning tasks, as evidenced by lower attack AUC scores. In terms of attribute unlearning, IDEA exhibits the lowest average loss values across different unlearn ratios, indicating its superior performance in this task as well. In addition to its effectiveness, IDEA also shows significant efficiency improvements over other baselines, especially when dealing with larger unlearn ratios. The running time of IDEA is not sensitive to the number of nodes to be unlearned, making it a practical choice for real-world applications. The paper also discusses the theoretical aspects of certified unlearning, which is an essential concept in machine unlearning. It highlights the importance of providing theoretical guarantees on the unlearning effectiveness, using parameters such as epsilon and delta to describe the proximity between the retrained model parameter distribution and the approximated model parameter distribution in the model space. The authors note that various techniques have been proposed to achieve certified unlearning, but they primarily focus on standard neural networks, leaving a gap in the development of such techniques for GNNs. Overall, the proposed framework IDEA offers a flexible and efficient solution for unlearning in GNNs, providing a promising direction for future research in this area. This paper introduces IDEA, a flexible framework for certified unlearning in graph neural networks, GNNs. Unlike existing methods, IDEA can handle various types of unlearning requests and provides theoretical guarantees for unlearning effectiveness. The framework is based on the analysis of the objective difference before and after removing certain information from the graph. GNNs have been widely applied in various fields, but they face the risk of privacy leakage, where private information is encoded in the training data. Existing unlearning approaches for GNNs only provide empirical results without theoretical guarantees. To address this issue, the authors propose a certified unlearning framework for GNNs, which can handle different types of unlearning requests, including node, edge, and attribute unlearning. The authors discuss the limitations of existing certified unlearning approaches for GNNs, which can only handle limited types of unlearning requests. These approaches are also restricted to specific GNN structures or objective functions. In contrast, IDEA is a flexible framework that can handle various unlearning requests without relying on specific GNN structures or objective functions. The authors also provide an effectiveness certification for IDEA, which ensures that the unlearning process is successful. The certification is based on the analysis of the objective difference before and after removing certain information from the graph. The paper concludes by discussing future directions, including extending the proposed framework to other tasks, such as graph classification, and studying GNN unlearning under a distributed setting. The authors also acknowledge the support of various funding agencies and organizations. The references provided in the paper include a comprehensive list of existing works on GNNs, machine unlearning, and certified unlearning. The authors also cite various papers on graph neural networks, including their applications, architectures, and training methods. In terms of technical contributions, the paper proposes a novel framework for certified unlearning in GNNs, which can handle various types of unlearning requests. The authors also provide a theoretical guarantee for unlearning effectiveness, which is a significant contribution to the field of machine unlearning. Overall, the paper presents a significant contribution to the field of GNNs and machine unlearning, providing a flexible and certified unlearning framework that can handle various types of unlearning requests. The paper also discusses the limitations of existing approaches and provides a comprehensive list of references to existing works in the field. Here is a combined summary of the 2 pages. The authors introduce the experimental setup and implementation details of their proposed framework, IDEA, for certified unlearning in graph neural networks. They provide information on the real-world graph datasets used, including their statistics, and the experimental settings, such as the training and test node set split, learning rate, and number of epochs. The implementation of IDEA is based on PyTorch and optimized using the Atom optimizer. The authors also introduce the baselines used for comparison, including retraining, graph eraser, certified graph unlearning, CGU, and certified edge unlearning, CEU. The authors then present the proofs for the propositions and theorems in their paper. Proposition 1 states that the localized equivalence of training nodes holds when the objective function is computed over the graph G and the unlearned instances delta G. The proof shows that the embedding of a node is only determined by its hop neighbors, and therefore, the objective function is equivalent for nodes that are not in the hop neighborhood of the unlearned instances. Lemma 1 states that the optimal solution to equation 3 equals the optimal solution to equation 2 when xi equals 1 per meter. The proof shows that the 2 equations are equivalent when xi equals 1 per meter, which means that the optimal solution to equation 3 is also the optimal solution to equation 2. Theorem 1 states that the approximation of the optimal solution using the infinitesimal residual brings a first-order infinitesimal residual with respect to the norm of the difference between the 2 solutions. The proof shows that the Taylor expansion of the gradient of the objective function can be used to approximate the optimal solution, and that the infinitesimal residual is of the order of O, xi caret 2, plus O, theta th. The theorem provides a guarantee on the accuracy of the approximation. The authors also provide information on the packages required for implementation, including Python, PyTorch, and other libraries. They also introduce the threat models used for evaluation, including MIA Graph and Steel Link. The paper presents a novel framework for certified unlearning in graph neural networks called IDEA. This framework provides a flexible approach to unlearning by considering both node and edge unlearning requests. The authors first define the concept of certified unlearning, which is a process that aims to remove the impact of a subset of data points from the trained model. They then introduce the idea of serializability of approximation, where any mixture of unlearning request instantiations can be split into multiple sets of unlearning requests that satisfy certain conditions. The authors also present 3 theorems that provide bounds on the L2 distance between the optimal points of the original and retained graphs. The first theorem gives an upper bound on the L2 distance, while the second theorem shows that any mixture of unlearning request instantiations can be split into multiple sets of unlearning requests, achieving upper bounded error. The third theorem demonstrates that the proposed model IDEA is an epsilon-delta certified unlearning process, with epsilon and delta being parameters related to differential privacy. The supplementary experiments include evaluations of bound tightness and unlearning efficiency. The evaluation of bound tightness compares the proposed IDEA bound with other baselines, such as CEU worst bound and CEU data-dependent bound, across various unlearning ratios. The results indicate that IDEA consistently provides tighter bounds than CEU, especially for higher unlearn ratios. The evaluation of unlearning efficiency compares the running time of IDEA with other baselines under edge unlearning tasks. The results show that IDEA achieves significantly less running time compared to the retraining approach and costs less running time compared to other baselines, demonstrating its efficiency in unlearning tasks. In conclusion, the paper introduces a flexible framework for certified unlearning in graph neural networks, providing upper bounds on the L2 distance between optimal points of the original and retained graphs. The supplementary experiments validate the effectiveness of the proposed model IDEA in terms of both bound tightness and unlearning efficiency, highlighting its potential for real-world applications requiring efficient and accurate unlearning processes. The paper presents a novel framework, IDEA, for certified unlearning in graph neural networks, GNNs. It focuses on the importance of unlearning in machine learning models, particularly in GNNs, which have been increasingly used in various applications. The authors introduce the concept of certified unlearning, which ensures that the model's parameters are provably updated to reflect the removal of certain data points from the training set. This is crucial for privacy-preserving data deletion and model retraining. The authors demonstrate the effectiveness of their proposed framework through extensive experiments on multiple datasets, including Quora, CiteSeer, PubMed, and CS. They evaluate the model utility by comparing node classification accuracy between IDEA and retraining, showing that IDEA sacrifices limited utility compared to retraining across different unlearning ratios. Additionally, they assess the unlearning effectiveness by evaluating node and edge unlearning tasks, as well as attribute unlearning tasks, using GCN as the backbone model. The results indicate that IDEA outperforms other baselines in terms of attack successful AUC scores and average loss values, validating its effectiveness in performing unlearning tasks. The paper also discusses the running time of edge unlearning on the co-author CS dataset, where IDEA shows significant improvements over existing methods. Furthermore, the authors provide additional evaluation results for node classification accuracy and unlearning effectiveness, further reinforcing the efficiency and efficacy of IDEA. In conclusion, the paper introduces a flexible framework for certified unlearning in GNNs, providing a comprehensive analysis of its performance on various datasets and tasks. The proposed method, IDEA, demonstrates superior unlearning effectiveness and model utility compared to existing approaches, making it a promising tool for privacy-preserving data deletion and model retraining in GNNs.